Hello everyone, welcome back. In this video, I'm going to talk about Hadoop and only the theoretical part of it. There won't be any hands-on on Hadoop. This is going to be our agenda. So I'll talk about what is Hadoop, followed by the components of Hadoop, which are MapReduce and HDFS. We'll also see how MapReduce works, and then I'll talk about Yarn, which is a cluster manager on a very high level, and then I'll conclude this video with the ecosystem that is built around Hadoop, which you have already seen, but it'll be part of a recap. So what is Hadoop? Hadoop is a framework that is used to store and process large data sets. So if you see, the definition matches with big data and data analytics. And Hadoop is the one which started the big data revolution. It comes up with two components. One is HDFS, which is the distributed storage, and MapReduce, which is the distributed compute. This is the same diagram that we have already seen in our last video, that is the introduction part. The distributed storage, which has metadata node or master node and multiple data nodes, wherein the data is split and stored in its own storage nodes. So if you want to map that with the HDFS, name node is the metadata node in HDFS, and then we have multiple data nodes whose information are stored in name node. Now let's see how HDFS stores data. So I'll take only four blocks for four data nodes. So data node 1 contains orange block, data node 2 contains blue, 3 contains green, and 4 contains yellow block. Hadoop gives high availability out of the box, meaning that the orange node would be available in other nodes also. So in this case, data node 2 and data node 4. Same is the case with blue, which will be available in data node 1 and 3. Green would be available in 1 and 4, and yellow would be available in data node 2 and data node 3. I have selected these nodes randomly, but you get the idea what I'm trying to say. HDFS provides high availability out of the box. Now if you see here, even if data node 1 goes down, we still have the orange block available in data node 2 and data node 4. If let's say data node 1 and data node 2 go down, even then we have all the blocks available, red, blue, green, and orange, in data node 3 and data node 4. So this is how HDFS not only distributes the data, it provides high availability also out of the box. The default block size of HDFS is 128 MB. Let's see how a client reads data from HDFS. Let's say I want to read this, or this HDFS client want to read this orange block. So what the client would do, it would send a request, a read request to the name node. Name node would say that the orange block is available in data nodes 1, 2, and 4. It will also mention that which one is nearest to HDFS client. So let's say data node 1 is nearest. So HDFS client will go and get the orange block from data node 1. So this is how individual blocks or records are read in HDFS. So let's take a look at the right path also. We have the same HDFS client, name node, and data nodes. So HDFS client would ask where to store this particular data. Name node would say, please store the data nodes in 2, 1, and 4. And then HDFS client would go and write in data node 2, data node 1, and data node 4. So all the three writes are done by the client itself. What about MapReduce? MapReduce is a programming model or programming framework that does distributed processing of data, or distributed data in this case. So this is part of distributed compute in a way, because the program uses the distributed compute environment to execute its code. The major programming languages of MapReduce are Java, Python, and Ruby, Java being the more prevalent. The framework does a lot of work for us out of the box. So when you talk about how MapReduce works, we'll see that the framework itself manages a lot of stuff which we do not have to do. There are two main components or two main phases of MapReduce. One is the map phase, and then is the reduce phase. Let's take a look at map and reduce separately. What it does is, processing is divided into two distinctive phases. One is the map phase, and the other one is the reduce phase. In the map phase, we write map functions which are actually written by us based on the application or workload requirement. Similarly, we write the reduce function also, that would be dependent on the business requirement or application requirement. The input to the map phase is the raw file, which is basically the distributed file. So I talked about 1 terabyte of data set, so which is broken down into multiple pieces and stored into different storage nodes. So input to map phase is that distributed data set. And input to reduce phase is actually the output of map phase. So map phase does some execution. That execution is essentially done by the map function, which is written by us. And the output of the map function is taken as input to the reduce phase, wherein we write the reduce function, and the processing is done based on the code that we have written. So this is again high level overview. We have that input file in HDFS, that is the distributed storage, which is fed into the map phase where the map function runs, and the map function generates output. The output is fed to the reduce phase wherein the reduce function runs, and that does some aggregation and then puts the records in output, which is again in HDFS. So I have shown here HDFS. It can be any distributed storage like Amazon S3, Google Cloud Storage, or Azure Blob Storage. So let's take a detailed look of the map phase. So let's say this is my file and these are my records. The map function, which is user written, reads each record one by one and then generates output, which is based on key value. Now this map function would run on all the nodes which are available in your cluster, the data nodes or the task nodes that I was talking about. On each node, the map function would be responsible for the chunk of the dataset that is available on that particular node itself. So it will read the records only for that particular chunk, and then it will output a set of key value records. And if you want to write the functionality of map in an equation, this is how it would be. So the input is key and value, and the output is a list of key, a separate key and separate values. Then you have the reduce function. Input to the reduce function are the key value records which were outputted by the map function or the map phase, and then it will be passed to the reduce function, and the reduce function will do all sorts of aggregation, and then it will generate the aggregated output which would be written back to the distributed storage. Now if you have to put it in an equation, this is how it would be. The K2 and list of V2 is the output of the map phase, and it will be converted into list of K2 and V3. Now let's take a deeper look on how MapReduce works. The first thing, obviously we have the input file, and what happens is the input file is automatically split into splits by the framework itself. So each split is equal to the size of HDFS block, which is by default 128 MB. Then the framework would create map tasks for each individual splits, meaning that each split would be processed by one map task. Now all of these map tasks are running the same map function, but working on different data, because split 1, split 2 and split 3 will have different data. So that's how the data would be different, but the code would be essentially the same. Now this map tasks would output key value records which will be stored locally. So these are local disks. Now why locally? Because it does not make sense to put the data output of map task rather in distributed storage, which will be an overkill. And also the work would increase, the time would increase. After it is put to the local, a number of partitions are created by the framework itself, and each partition would be taken up by one reduce task. The number of reduced tasks would be similar to or would be equal to the number of partitions. Now a lot of things are happening here in this particular area, which we'll talk in the next slide. One more thing I want you to remember is that all these things are happening on a single node. So the splits are on single node. These splits are not similar to the chunks that I talked about in the distributed storage. So these are happening on a single node. This input file is essentially the 200 GB of chunk that I was talking about, which will be further split by the framework itself, by the MapReduce framework itself. All right, continuing from the previous diagram. So we have these map outputs. So these are key value outputs. We'll have one key and its corresponding value. And the framework would actually sort these outputs by the key. So the key value output would be sorted based on the key itself. Again, this is done by the framework. We do not have to write any code for this. The only code that we would write would be the map function and the reduce function, and everything else would be taken care of by the framework itself. So after the map output is written to the local disk, that output will be sorted by key, and after that it will be put into multiple partitions. Now a partitioner would work here, which will take these key value pairs, which will take these key value records and put them into individual partitions. By default, the partition strategy is the hash partitioning, but you can have custom partitioning strategy also. So the partitioning is done by the key, and this is the map side of things. After the partition is done, it will be copied over to their corresponding reducers, which is called as the copy phase. So after it reaches the reduce side, it will do a merging of these partitions, because as you can see, there can be multiple partitions coming in from the map side to the same reducer. So partition number 2 and partition number 5 has gone to this reducer node. Partition number 1 and partition number 3 has gone to this reducer node. So after all the partitions are received, they will be merged together. Again, it will be done by the framework, and then it will be sent to the reduce task or the reduce function while maintaining the sort order. So this is called a shuffle phase. Then the reduce tasks would take the merged and sorted records as its input, and then generate the aggregated output. So this is the from merge till reduce task is basically the reduce side of things. Now all the coloring that you see, the sorting, the partitioning, merging, maintaining sort order on both map side and reduce side, these are done by the framework. We do not have to do anything, or we do not have to write any code to complete these phases, wherein you sort by the key and do the partitioning and send the partitions over to its corresponding reducers, and then merging and then sorting. So all the things that you see in color, those are handled by the framework itself. Let's take an example, which is a typical example of big data processing, the word count. So on the left hand side, you have this file which contains these words: deer, beer, river, car, etc. So what will happen is that this is a file which is there in one of the nodes. This is a chunk, the 200 GB chunk in one node. All these are part of a single node operation, and the same thing would be happening in all the other nodes in the cluster. So first, the file would be split based on the SDFS block size, which is 128 MB by default. Now, each individual splits would have its own corresponding map task. So if you see here, what map task is doing, it is counting the occurrence of the word. For example, in this split, I have deer, one occurrence of deer, one occurrence of beer, and one occurrence of river. Same is the case here. So for the second split, we have two occurrences of car and one occurrence of river. In the third split, we have one occurrence of deer, car, and beer. Now this is the mapping phase. After this is done, it will be sorted by the key and it will be partitioned. After the partitioning is done, each individual partition would be sent over to the reducer. Now there, the merging would happen. If you see the beer, all the beers are getting copied to the same reducer node. Same is the case with car, deer, and river. All of them are getting copied to the same reducer node because the partitioning was done based on the key, and each partition corresponds to one reducer task. So in this case, the partition with key beer would be taken up by reducer task 1. So now once merging is done, again the sorting would also happen. Now this is a very simplified example, that's why you are seeing only 4 words. There can be other words also here in the same node. Okay, so after this is done, it will pass to the reducing phase or the reduce phase. You can call it reduce phase, you can call it reducer or reduce task also. Then the reduce task or the reduce function or the reducer would do the aggregation. So there are two occurrences of beer, so that's why the number is 2. So essentially these are aggregations. Once this is done, the final result would be written back to a file which will be stored in SDFS or a distributed storage. So another component in MapReduce framework is partitioner. So what partitioner does, it creates partitions for each reducer. So partition will be created based on the key. So the number of partitions would always be equal to the number of reducer tasks. And the key with the same value would always land on the same partition. There can be two types of partitioners. One is the default partition, which uses hash function to put records in partitions. And then there can be custom partitioner also, meaning that we can create our own partition. Typically, default partition would work most of the cases. There is one more component which is called combiner. You can think of it as mini reducer. Combiner also runs at the map side. You'll code combiner by extending the reducer class itself. So what it does is you run the combiner function on the map outputs. So the advantage of combiner is that it reduces the amount of data that has to be moved over the network during the copy phase. Let's take a relook at the entire flow of MapReduce. So we have this file. The split of the file is sent to a map task which creates its own output. Then you sort it by key. After it is sorted by key, you run the combiner on top of it, which acts as a mini reducer, and it will reduce the record by aggregating on that particular map output. And after that, the partitioner is run. So you can have your custom partition or default partition. Once this is done, you'll have the copy phase kicked in, which will move the data from mapper to the corresponding reducers. And on the reducer side, you get the input from mappers. You merge and maintain the sort order and run reduce function on those particular records and generate the output. So combiner and partitioner work on the map side only, not on the reduce side. So if you see, the functionality at the reduce side remains the same. There are no additional components, but you can have combiner and partitioner at the map side. So I wanted to do a recap of the distributed processing. So if you remember, all the nodes would complete their work and send the output to the metadata, which will send it back to the client. The reason for this recap is to talk about Yarn, which is a cluster resource manager. Yarn have multiple APIs to work with the cluster resources, but we as developers do not bother about it. We let Yarn do its work by managing the cluster resources. So let's see how Yarn works. The diagram would be more or less similar. So on the distributed storage side, you had name node and data nodes. In distributed processing, we had job and task. And in Yarn, we have resource managers and node managers. The reason the diagrams are similar or the architecture are similar, the components are more or less similar because all of them run on the same cluster. So the concept of master node and or metadata node is there in all the components. For HDFS, it is called metadata node. For distributed computing, it is called the job node. And for Yarn, it is called resource manager. So this is how Yarn works. So let's say you have client or applications. You have written codes on MapReduce or Spark. When you submit the job, you submit the application to the resource manager. So what the resource manager does, it goes and selects one of the node managers and creates a container which would run something called application master. Once the application master is started, it will ask resource manager for more resources, meaning that the application master would say to the resource manager that I need more resource to execute the code in a distributed fashion. So resource manager will say, okay, you can go ahead and work with node number 1 and node number 3. So then once it receives the input from resource manager, the application master would start containers on these nodes where the actual application code would run. So the orange containers are the places where your actual code would run. I have intentionally kept this node as blank because there might be cases that some of the nodes are not running anything. So this is how Yarn works. Now all the programming model or framework that runs on top of HDFS using Yarn use the same functionality. The programming flow or the execution flow is similar, exactly similar to what I'm showing you here. Remember, first it creates something called an application master. Application master asks for more resources from the resource manager, and resource manager says, okay, you can go ahead and create containers in node number 1 and node number 3. Then application master goes and creates the container in these nodes and runs the actual code. In case of MapReduce, the map function and the reduce function. So let's recap the Hadoop ecosystem again, because I think after giving you a high level overview of Hadoop, it would make a little bit more sense now. So we have HDFS at the bottom. We have Yarn, which does the cluster management. We have MapReduce, which is a programming modular framework. Hive runs on top of MapReduce. There are other programming frameworks also like Stays and Spark. Spark does not use MapReduce. Stays also does not use MapReduce, but they use Yarn for cluster management and runs on top of HDFS. One interesting thing that I have missed here is that Hive can run on top of these also. There are other frameworks and execution engines who do not use Yarn at all. They run directly on top of HDFS like Presto and HBase. These execution engines do not use Yarn as their resource manager also. That's all about Hadoop theory. See you in the next video. Thank you.